Hi, today we're going to talk about continuity. So we'll start with the definition. A function f of x is said to be continuous at a number a if the limit as x approaches a of f of x equals f of a. Now this definition implies three conditions must hold true. First of all, f of a has to be defined, which means when you plug a into your function, you have to get a real defined value. It also implies that the limit as x approaches a of f of x exists. Now remember, for a limit to exist, your upper limit and your lower limit have to match, and they have to come at the same finite value. And then that third condition, which is part of the definition, says not only is your function defined and the limit exists, they give you that same finite value. Now, if a function is not continuous at a, then we say that f of x is discontinuous at a, or we say that f of x has a point of discontinuity at x equals a. Now, if f of x is discontinuous at x equals a, but the limit exists, which means your upper and lower limits match, they meet at that same point, well, then the reason your function would not be continuous is because that limit does not equal your function evaluation. That is called a removable discontinuity. So here are a couple graphic examples. Now notice the limit from the left and the limit from the right match, but the function evaluation doesn't. Here the same thing, and here there isn't a function evaluation. These are referred to as removable discontinuities. And a way to think of that is it looks like they just essentially removed a point. Now, if f of x is discontinuous at x equals a because the limit does not exist, well, then that's called a non-removable discontinuity, and we have two types. We have our jump discontinuities and our infinite discontinuities. So our jump discontinuities means that the reason that the limit didn't exist, your upper and lower limits gave you single finite values, but those single finite values didn't match. So here my limit from the left and limit from the right did not match. So this is referred to as a jump discontinuity, and again, we're discontinuous because the limit didn't exist. Now for our infinite discontinuities, if you remember, one of the things that we discussed is that your function, what it means for your limit to approach infinity means your function is increasing positive without bound. Now, infinity is technically not a real number, so technically that limit doesn't exist because it's not a single finite value. So if your limit as x approaches a of f of x equals infinity, that's just saying your function is increasing positive without bound. So technically that limit doesn't exist, so by definition your function is not continuous there. And these are examples of infinite discontinuities. Now, if function is continuous from the left at x equals a, if the limit as x approaches a from the left is equal to your function evaluation. So notice here the limit as x approaches -2 from the left gives me that function evaluation. We would say this function is continuous from the left at x equals -2. A function is continuous from the right at x equals a if your upper limit, or the limit from the left, or from the right, equals your function evaluation. So notice the limit as x approaches 1 from the right gives me the same as my function evaluation. This function we would say is continuous from the right at x equals 1. I'm going to quickly introduce you to a new function called the greatest integer function. It's also known as the floor function. And it's defined as the greatest integer that is less than or equal to x. So for example, f at 2.5. What is the largest integer that is less than or equal to 2.5? Well, there are infinitely many integers that are less than 2.5, and I want the largest one. So one of the things that we can do is draw a number line and plot where 2.5 is, and then just look to the left. And what's the first integer you see to the left? 2. The greatest integer that is less than or equal to -4.7. So again, we look to draw it on a number line, find where -4.7 is, look to the left, and the first integer you see right there, the largest one, is -5. Now the greatest integer that is less than or equal to an integer itself would be itself. So the greatest integer that is less than or equal to 1 would be 1. So again, you can draw these on a number line. Here's 2.5, look to the left, the largest integer is 2. Here's -4.7, look to the left, the largest integer is -5. Here's actually what the graph of this step function, the greatest integer function, looks like. Now technically, if you take the limit as x approaches -3 from the right, it gives you the function evaluation. If you approach the limit as x approaches -2 from the right, it gives you the function evaluation. But if you approach the limit as x approaches -2 from the left, it does not give you the function evaluation. So this function, based on our previous definitions, our functions are continuous from the right, but not from the left. So where is this function continuous? We would write it like this, where these closed intervals means, hey, this is continuous from the right at -2, but it's not continuous from the left at -1. It's continuous from the right at -1, but it's not continuous from the left at 0, and so on and so forth. So what does it mean for a function to be continuous on the interval? It means it's continuous for every single number on that entire interval. Now we have to understand that continuous at an endpoint of an interval means it's continuous from the right or continuous from the left, like the example we just went over. So let's look at a big graph. Let's determine where is f of x discontinuous, what type of discontinuity is it, and then let's sum up and determine where it is actually continuous. So here's a random graph that I drew for you. Now when you're looking at continuity graphically, one of the things that you can do is trace it with your pencil. So as you're tracing, anytime you have to stop to lift up your pencil, right? We can't go through an open circle, it's not inclusive. We'd have to lift up our pencil to draw this point and come back down, or even if this point wasn't here, we would still have to lift up this pencil to continue the graph over here. As soon as you have to lift up your pencil, it is a point of discontinuity. We'll notice this limit exists, right? The limit from the left equals the limit from the right. The issue is the function evaluation doesn't match. So we would say x equals negative, that should be -2, is a removable discontinuity. X equals -2 is a removable discontinuity. It looks like I removed that point. So continue tracing, and again, as soon as you have to lift up your pencil, can't go through an open circle, I'd have to lift up my pencil to color this dot in and lift up my pencil to continue here. Then as soon as that happens, you have a point of discontinuity. So x equals 1 is a point of discontinuity. Why? Because the limit doesn't exist. But the limit from the left is a finite value, and the limit from the right is a finite value. They just don't match. So x equals 1 is a jump discontinuity. Draw with your pencil. We can't go down forever because we can't actually get to -infinity. But we would have to lift up our pencil to come to get to this other side here. The limit doesn't exist because technically the limit from the left goes to -infinity. The limit from the right goes to positive infinity. They don't match. But also infinity isn't a real number, so this is a non-removable discontinuity, and because your function is shooting off to one of the infinities, it's an infinite discontinuity. So that's where this function is discontinuous. Well, where is it continuous? Basically everywhere else. Now notice your function from the limit from the left doesn't equal your function evaluation, neither does the limit from the right. Same thing happens here and here. So you are not continuous from the left or continuous from the right, so we would use all open brackets because we don't have any endpoint continuity. Now, if f of x is continuous and g of x is continuous at a and c is a constant, then the following hold true. So if these two functions are continuous, when you add them together, they're going to be continuous. When you subtract them, they're going to be continuous. If you just take a continuous function and multiply it by a coefficient, it will also be continuous. If you multiply two continuous functions, you get another continuous function. And if you divide two continuous functions, you get a continuous function, so long, again, as that denominator isn't equal to 0. Now, something we talked about a while ago, if function f of x equals a to the n x to the n plus a n minus 1 x to the n minus 1, so on and so forth, it's called a polynomial function of degree n. Now, here's a very important little note for you, and you need to reserve this somewhere in here and be able to recall this information. This is very useful. First of all, most functions are continuous on their domain. Polynomial functions are continuous everywhere, from -infinity to positive infinity. That's true for the nth root of x as well, as long as n is odd. If n is even, the nth root of x for an even root, that's going to be continuous from 0 to infinity. Because remember, you can't take the even root of a negative number. And rational functions, which are polynomial over polynomial, those are those fraction polynomial, or those fraction functions, those are continuous on its domain. So let's look at a few examples here. Where are each of these functions discontinuous? Well, let's look at f of x equals x squared minus x minus 2 over x minus 2. This is polynomial over polynomial. This is a rational function. And we just said rational functions are continuous on its domain. So let's find the domain of this function. Well, what rule are we in fear of breaking? Dividing by 0. So we know that x minus 2 can't be 0, which means x can't be 2. So this function's domain is negative infinity to 2 and 2 to infinity. So this function is continuous on that domain, which means it's not continuous or discontinuous at x equals 2. Here's what the graph of that function looks like, and as you see, it looks like we removed that point. That's a removable discontinuity. Let's take a look at this function, 1 over x squared if x is not equal to 0, and it's 1 if x equals 0. Well, this rational function is continuous on its domain, which is all values except for x, which is what we have here. And then 1 is continuous everywhere, so it'll be continuous at 0. So now what we need to know is, hey, is this function actually continuous at 0? Is the function defined? Does the limit exist? Do they give you the same value? So let's check those three conditions. So is f of 0 defined? Well, when I plug in 0, I get 1. That's a real defined value, so yes. Does the limit exist? Well, when you take the limit as x approaches 0 of 1 over x squared, coming from the left, little negative values close to 0 squared gives you a positive. You take 1 divided by a really small positive number, you get a really big positive number. Same thing coming from the right. So one of the things that we talked about previously is that 1 over x squared, as x gets closer and closer and closer to 0, x squared gets even closer to 0 faster, and 1 divided by a really small number gives us a really big number. That limit's actually infinity. So technically this limit does not exist, which means it's not continuous at 0. But also notice your function valuation and infinity don't match. So this function is discontinuous at x equals 0. And here's the graph of that function. Notice from the left we shoot off to infinity, from the right we shoot off to infinity, but the function evaluation's right there. So that's definitely a point of discontinuity. Let's do one more example. F of x equals x squared minus x minus 2 over x minus 2. We actually just determined that this is continuous for all values except for 2, but this function's only defined for those at 2. 1 is defined everywhere, so it's definitely defined at 2. So in order to check continuity, we just need to know, is it continuous at 2? Well, to find that out, we have to prove our three conditions. Well, first of all, is the function defined at 2? It certainly is. Does the limit exist? Now, when we take the limit as x is approaching 2, remember, that doesn't mean x equals 2. That means x is approaching 2. So if you're approaching 2 and you're not equal to 2, we're going to use this function right here. Well, direct substitution obviously won't work. But what we can do is use one of our methods from previous, factor, cancel like factors, and then try direct substitution. So this limit is actually equal to 3, which is a real defined value, so this limit does exist. But my function evaluation was 1, and my limit was 3. Those don't match, so that third condition, which is the definition of continuity, doesn't hold true. So this function is not continuous at 2, and here's what the graph of that function looks like there. So that's what it means to be continuous. So we're going to pick up in the next video with a few more examples of how we can actually make a piecewise function continuous at a particular value, and also something called the intermediate value theorem. See you next time.